Hey, well, people are filtering in for class. I'm not technically starting with the material, but I just wanted to get everybody's, or some of you folks' impression of the homework that was due. Hard, easy, in the middle, confusing?
Yeah, it's hard. Yeah, definitely.
Definitely confusing? Well, that's a really good point because what makes it confusing is it's real world stuff, right? And we all as engineers love it when everything can fit into a nice box that's easy to interpret and understand. But once you get out in the real world, it's not always easy. And so what you'll have to develop as you evolve as engineers is that practical, okay, here's information and what's relevant and what isn't relevant. And then we'll help you a little bit in terms of understanding how to process things. The other reason why I wanted to talk about real world is because this is a real physical transformer that actually is not far from campus. So I did Google Maps, and that's up here on the screen, and you can see actual physical location is about 22-minute drive from campus. So this is for a wind farm up in Passadumkeag. I'll zoom in a little bit, but I'll actually show you the transformer.
You don't want to do the homework the legitimate way. Take a drive.
You can drive up there. If you can get into the fence, though, you can see this is all fenced in all around it. But the transformer is right here. That is the data sheet of the transformer that you just analyzed. And I can't do a picture, like sometimes you can use Google Street Maps to actually be able to see more detail. That's about the best you can get. But yes, you could get onto the site because this is an open road. I don't believe they put a fence here. It's a pretty nondescript building, but to get inside the substation, I don't know if you can see. Yeah, it's pretty fuzzy, but there's a fence all the way around. And it's a combined owned substation. You can see there's a fence actually in the middle here. Kind of hard to see, but there's a fence in the middle. And that's because the lower substation is actually owned by Versant. And the upper substation is owned by the owner of the wind farm. So you can actually, and it's hard to tell, but you can even see like there's two separate control rooms. One goes to the lower portion and the upper one goes to the other one. And technically, they're not supposed to be able to go in each other's substation, right? Because it's separate property. So it's best to have it set up like this where they're physically adjacent to each other because you can actually run bus between the two. But it does make things complicated from a logistics perspective, which is this independent power producer owns their site, but they have to let the utility get access to certain pieces of information. So they actually have to drive on their site. So there has to be an easement and all that stuff. So yeah, and this project, they broke the line. So you can see there's two incoming sets of three-phase conductors. They actually broke the line. You can see that right here. Oh, why isn't this allowing me to annotate? I don't know why it's not annotating. Try that again. I don't know. It won't annotate. Oh, maybe now it is. So they physically broke, I think it's a 138 kV line right there. And you can see the towers that they actually ran into the facility. So that's all owned by Versant. So again, if you wanted to check it out, I mean, we can always maybe get a tour of the facility. Usually it's much, much easier to get a tour of the developer's facility or the generator's facility than it is to get the tour of Versant. And a lot of that has to do with what's called critical energy infrastructure information, which is basically if bad guys get information, they can do nasty things to the grid. So a lot of the stuff used to be readily accessible. You can get all kinds of information. Now it's under pretty heavy lockdowns. And it's not like, to the best of my knowledge, you're not going to go to prison like you would for releasing confidential information, government classified information. But, maybe that's going to come at some point. So the nice thing is it's just Google Maps, right? This is nothing confidential about it. Anybody can go and drive by the site and take pictures or run a drone over it and do what they need to do. So this is not protected. But let's go through the problem. So we start off over here because we need a bunch of information from this sheet. The first thing that I'm going to need is it's 60 MVA is the base rating of the transformer. Remember, we have additional ratings of the transformer if we turn on fans. most transformers are rated on a base rating. That's what their impedances are, primarily because that's what we know it's going to operate at. It may or may not operate at 80 or 100. It just depends on temperature and loading. So that's the first important part. The next thing was really helpful was looking at the winding information. We see that the 115 winding is Y connected, and the low voltage winding is delta connected. You'll also notice that there are some taps on the high voltage winding, and that's pretty common. They'll come with no load taps because it really doesn't cost the transformer manufacturer all that much, and it just allows you to goose up the voltage or goose it down a little bit so you can get better operating characteristics of what you want. Another thing, because some people were talking or asking about it, you'll notice the bushing identifiers. So if you take a look at the bushings, you'll actually see the high voltage bushings are denoted with H's, and the low voltage bushings are denoted with X's, okay? So you know it's a 115 to 34.5 kV, 60 MVA transformer. Y on the 115 side, delta on the low voltage side, and we'll talk a lot more about that when we look at what's called zero sequence filtering. With taps on the primary side, you normally only have taps on one side. So now we can actually start to go to the load loss or the no load test. We'll start off with the no load losses, sorry. And what we see is a bunch of data, as people were talking about when they were entering into class. And the reality of it is the no load test is the open circuit test, which says apply rated voltage to one of the windings and measure the current. Rated voltage is 34.5 kV. So to gather your data, you should have been using, oops, that row right there, right? You don't want to run it at 20,700 volts because is that rated voltage? Not even close. So you wanted it to be that value. So now you can see that I've applied, because it says terminals A, B, and C. It tells you X1 to X2, X2 to X3, X3 to X1. That's where the voltage was applied, okay? And then they measured a current. They measured current flow in those three terminals. The hard part, though, is when I do my open circuit test, or no load test, I need to do, we'll call it open circuit test. I need to do V no load divided by I no load, right? This is my angle of Z. This is my angle of negative theta. But I've got three currents there. Which one do I use? I don't know. I just picked the average. So I took the average of those three, came up with my number. That's all I did. But here's where I got to be careful, because on a delta, right, here's my transformer and my delta windings. I'm measuring this current, which is a line current. The actual impedance I'm trying to get is in that leg. So that's a phase current. So I have to take the no load average and divide that by the square root of 3, right? I've got to convert that to a phase current. Now, the voltage over here is a line voltage, but that's also the exact same voltage across that individual element. So in this case, I don't need to divide the no load voltage by the square root of 3. I've got the answer, right? So it's just V no load at an angle of 0 divided by the average of those currents. That becomes I no load, but a line current. And then I got to divide that by the square root of 3. The only thing I need to do is solve for theta. Well, I can see that I've got a power 42.312. That's a three-phase power. I've measured all three phases. So I've got 42.312 for my power triangle. This value of S is equal to V no load times the I no load average. And then I multiply that whole thing by the square root of 3, right? I'm looking at the average of the I know load, not the phase current, not the divide by the square root of 3. And when I do that, I end up with theta there. Okay. And when I've got that, now I can solve for my Y open circuit, which is I no load divided by the square root of 3 at an angle of minus theta, divided by V no load at an angle of 0, and that's equal to 1 over R sub C plus 1 over J X sub N. That's the no load test. Now I've got 2 out of the 4. Now I'm going to go to my load loss test. So over here, I'm going to use my base transformer rating of 60 MVA, and I'm going to use my nominal tap position, which is right here. So that tells me the voltages, or the 3 voltages that I have. I also know what the current is, and I'm going to go ahead and do my total power that is corrected. Not the measured, but the corrected power, which is temperature corrected to 20 degrees C. Okay?
I have a question.
Yes.
So,
Because it tells me it's tap position 3, right? That's in the intermediate tap position.
okay.
So that's where I know it's the 115 kV. You can also go up over here and you can even see windings resistant, turns ratio. And then I go past it. It should tell me the tap positions too. 1, 2, 3, 4, 5. Let's see if I might not have had it up on the screen. No, I'm getting closer. Okay, so if you see here, you see tap position 3. What do you notice? The voltages are exactly the nominal voltages. Okay. So now I'm going to do my short circuit test, which I've got my V no load, which is at an angle of 0, divided by my I no load, which is at an angle of theta. This is a Y connected winding, right? Because this is on the 115 kV side. How do I know it's 115 kV? It tells me. It tells me it's on H1 to H2. That's where the test was applied, which was the high voltage winding we saw at the beginning, on page 2 of the report. So this is the high voltage winding. So I'm going to draw a picture showing my transformer windings. And the voltage that is applied is here. But I'm looking for the parameters associated with that. So I need to divide this by the square root of 3 to be able to get the actual voltage across that element. And the current that I measure is here, but that's the same current as here. So I don't have to do anything with calculating my current, right? It's already set up. It's already, the line current and the phase current are the same in a Y. So finally, I had to do another power triangle. So this here is 112.9. And this is S equals square root of 3, V no load, I no load, which gives me my angle of theta. Once I have that, V no load at an angle of 0, divided by I no load at an angle of minus theta, don't forget the square root of 3, equals RE plus JX equivalent. There's one last thing you need to do to get the answer. This short circuit test was on the 115 kV side. This one over here was on the 34.5 side. So if you're going to draw your equivalent circuit, you needed to draw it like this. Right? Those impedances are like that. So this is the 115. and this is the 34.5, or you could have drawn it this way, and you can pick whichever winding you want. Whoops. You can reflect them over to one side or the other transformer. You just have to reflect one pair of data points there. So either R sub C and JXM get reflected to the high side, or RE and JXE get reflected to the low side. Okay. Here is the MATLAB file. That solves for it. So you can see I did the no load. I took the average for the currents. I grabbed my P no load, my V no load, then my S no load, square root of 3 times those. Then I calculated theta, I called it no load. Then I solved for Y. Notice, right? I took my I and divided it by the square root of 3, which means I just moved it into the denominator. It's the same thing. Multiplied by my V no load, which has no angle. And then I associated my R sub E and XM. Then I moved those impedances to the high side of the transformer using the turns ratio squared. That's all I did. So I actually showed those on one side of the transformer, on the high side. Then I did the same thing for the short circuit test, but I found the averages of the voltages. I've got my P, my I, calculate S. Then I go ahead and get theta and Z, and I'm good to go. So I'll run this. Remember, there's clear in CLC. There's nothing up my sleeves. And whoops, that's not what I wanted. There's your answer. I have R sub C, 84K, X sub M, 95K, but those are on the low side. On the high side, it becomes 94 and 106, right? K. Oh, no, sorry, this is 94, and this is actually not 106. This is 1060, essentially. And then RE and XE are already on the high side, so there's nothing I need to do. And the last thing you can check, right? No, we know how to do per unit calculations now. So the last thing I did was calculate my Z in per unit. So I took the combination of these two, I vectorially added them together, and then divided by Z base, and I got 0.94. Is that correct? What do you know? Tells me 9.4% right there. So this result here checks out with my data sheet. See how these two are the same? 9.4% is 0.094. Yes, sir.
So I was done with one of the values using the formula.
That's fine. You can do that too. Yeah.
If you look at the chapter 3, page 1.
Yep. Yeah. If you just, yep. I mean, it probably is just a precision thing, is my best guess, although it shouldn't be that far up. It should be, did you do I squared R, I mean, V squared over R equals the resistance or the power? I'd have to check it. I don't know. Because I know that if I have a transformer, that was for the open circuit test, right? So all I have is this. I know that if I have the voltage over here, that the power consumed in that circuit is going to be V squared over R sub C. But I got to be careful. This is a three-phase power. I had better divide that power by 3, right? To make sure I convert it to single phase. And you still got 300K? I don't know. That's what I would have done. And you used so what I would have done is, what was the power? Was it 42.1? Yeah. Well, here's the power, right? It's 42.1 is the no load power that's consumed. That's going to be equal to 34.5 K. That quantity squared divided by R sub C. So R sub C should be equal to times, not squared, not times 2, but times 3. Say that again? Yeah, because it's 42.1 K divided by 3. So I just inverted and multiplied. Did I make a mistake in the algebra? Do you want me to do it in MATLAB? Would that be helpful? Anybody? Let's just do it. So I'm going to do 34.5 or just 3,500 squared, multiply that by 3, and then divide that by 42,100. And I get about 85K, which compares pretty closely, right? Isn't that the same amount? I have to. That's where the test was done on, right?
This slide is.
Because the test was done at 200 kV. Right? This was done on the 200 kV side. This was specifically done on the low voltage side, right? That's not a very confident yes. Look over here. It tells you it is done at 34,500 volts. That's where the actual test was performed. Where the other one was the test was performed on the 200 kV. And if you remember when we talked about doing these practically I can go out and buy a 35,000 volt test source much easier than I can buy a 115,000 volt test source. Are you sure?
Yeah, I was dividing.
That's the same thing.
You did 34.5.
So what I did, it's just algebra, right? So you can see here, let's go to this equation right here. This over here, right? P30 equals V squared over R sub C times 3, right? If I multiply both sides by 3. So then to solve for RC, it's V squared times 3 over P30. It was the algebra, right? I just did it too quickly.
Yeah.
Questions? On the high side or the low side? Either one's right there. 951,000 or 1.06 meg. Was this too hard of a problem? Yes, sir.
Oh, well, that MATLAB script be in practice.
If you want it to be. Was this problem too hard? You can be honest. Doesn't hurt my feelings. Yeses?
I don't think it was.
Okay.
The numbers.
A lot of data.
Yeah. Yeah.
But this is, so here's the hard part about teaching this class. Most of you are graduating in what, 6, 7, 8 months? This is real world stuff. Nobody's going to walk up to you with a very simple transformer test with the exact data you need. They're going to be, here's the test report, figure this out. So what I'm trying to do is bridge what we've been teaching in class into real world and try to give you a few nuggets, right? Like I told you at the beginning of the assignment, hey, look at the load loss and the no load loss test, right? And I think he even said use the 60 MVA. So at that point, then you got to start parsing through the data to figure out what we need. Once you see there's a lot of data, then the hope was, okay, what is this winding? And nobody asked me the question saying which one to use. Well, a couple people asked me today, but nobody said which winding, which data. I don't know which one to use. And then we would have talked that through, and then hopefully that makes sense. So, that's the intention. We do like the next homework, your per unit one is all based on real world stuff, a lot of different data. The per unit diagram I'm asking you to do is for a facility in Millinocket. It's more than 22 minutes away, but it's a hydroelectric facility that you'll be doing. Why? Did you have a question? Okay. Anything else?
Took a look at the per unit, homework,
Yep.
and I thought like with the full file, it's a bunch of documentation.
Yes.
But I didn't see like any like question on it, so are we just doing like a per unit analysis?
I want the per unit diagram. Yes, I'll bring that up. And so where is the diagram? So I want a per unit diagram of this. And the nice thing is you only have a couple buses, right? There's a bus right here. We'll call that bus 1. If you look over here, there's another bus because there's a transformer 2, 3, and 4. The only things you need to worry about, I need impedances for that because breakers don't have impedances. These are breakers, right? You can see it's a 1200 amp breaker. That's a no impedance device. So the transformers have impedances and the generators have impedances. And that's it. So all you need to do is the per unit diagram for that. You don't need to worry about these connections here. Those are how we connect the generator neutrals to ground. Those can be, that would be a harder concept to understand if I asked you to do that today. Eventually you'll be able to do that. But right now, just assume that those generators just are solidly connected to ground. It's not going to matter when you do the 3-phase per unit diagram. Those don't matter because what we've learned, right, is in a balanced system, we don't actually have any neutral current. So you can ignore those. I will say for the generator impedances, because if you look at the generator data sheet, so there's a lot of data. I only want you to use the XD, and I would use the saturated values here. So not all the data sheets, just to use the XD to model the impedance. So you're going to steal the impedance from there. Okay. So rather than just give you the specific stuff, going through the data sheet will help you realize, okay, this is maybe relevant, this is not relevant, that type of stuff. Okay.
This is kind of like what we did in lab.
Exactly. Yep. Just not as cut and dry, right, with the material. Any other questions? I would have thought everybody would have been like, wow, we have a test a week from yesterday. Nobody saw that. Or maybe you're not worried about it. You have a question?
Oh, I had a question about review day.
Review will be on Thursday.
Thursday? Okay.
So if you look, there's already in the folder, there's already a review sheet to help you study. Yes, sir.
On the stuff about the test, it says you may have a piece of paper and a calculator or MATLAB.
Yes. So you can have a piece of paper with the calculator or with MATLAB, either one.
Okay, I was wondering if that and the president.
No, it's not a parentheses. It's not a parentheses around those.
If you got a piece of paper, then no MATLAB.
Nope. You can do either one. I just want you to use MATLAB as your calculator or your calculator as a calculator. It's your choice. And I know some of you using the TI 30 or 36 matrices are very tough to use with those. I mean, I shouldn't say very tough. They're not as simple as we're doing with MATLAB, but I don't expect you to be MATLAB experts. So if you want to use a calculator, you're welcome to do it.
So if we're using MATLAB, you're okay with us like having our computer open using
Yeah.
MATLAB? while we're taking-
I walk around a lot. I'll be able to tell if you're using the Alt Tab button, you should have MATLAB up exclusively. If you're using Alt Tab and you're bringing up other stuff, that's a problem. Right? Because just like your calculator, put your calculator right here, right? You're not flipping and doing different things. MATLAB would be the screen that you'd have up. And I don't want you to upload script files. If you want to get a answer or grade for your answer, I don't want you to just say, see MATLAB file. I want to see your work. And then MATLAB is your calculator. So just like you would do it in paper, don't say, okay, here's the script file. It's like, no, I don't need to see that. I just want you to use MATLAB as a calculator. So all the work to get your answer has to be spelled out on paper that you turn in. And then you say, just like you would from your calculator or MATLAB, the answer is 22.6. I don't want you to say, oh, refer to MATLAB with a script file, because that you could have copied that from something else. I want to see the paper, the hand stuff, and then you do your calculations in MATLAB. Yes, sir.
That being said, is it okay if when doing the calculations in MATLAB, we use a script file?
You can write your own script files, yes. Yeah. That's what I would do. But you can run the editor, right, in MATLAB, right? So that's fine. I just don't want people to open up script files and try to do that stuff. That's why I don't accept script files for a solution. I've got to see handwork. I don't want to see any MATLAB submissions when you do your test. All I want to see are handwriting stuff. That applies for people in TV land, right? Because you could just do script files and dump it out. I don't want to see those. I just want to see your numbers. Yes, sir. Yeah, that's fine. I didn't mean to make everybody nervous. I just would have thought people would have been like, oh, we have a test on Monday. Is that right? Maybe people didn't notice it. I don't know. Did people not notice it was a test announcement? I did make an announcement, right? It's in the schedule too, as being next Monday. So hopefully nobody was caught. Maybe that's why nobody was worried about it, not caught off guard. But if you look on Friday, there's already a review. So we'll do a review on Friday because Thursday, because that's our last class together before you have the test, right? The test will be in here during lab. So if you want to take it online, let me know in advance. If you can be here, it's usually better because I can answer questions. It's harder to do questions on, well, it's not harder, but it's harder to sometimes see what people's work is. I can set up rooms, meeting rooms individually, so I can talk with people, so I can see their work and they can share it. But usually if you're near campus, it's better to do it here. Okay?
You get like a one sheet or?
You get to write your own. That's what the 8.5 by 11 is. Probably not a lot of formulas, right, on this one? Because a lot of the stuff, oops. Why is it doing that? Sorry. I guess it hasn't figured out that there's a separate screen.
I have another question.
Yes.
If we're using MATLAB, are we allowed to bring the scripts that we wrote beforehand?
No. No scripts. Because that doesn't show what you've learned, right? That just shows, something you copied over. That's why I don't want to see scripts. I want to see your handwork. Bringing scripts would be basically like bringing additional pieces of paper, right?
I was thinking like, if I know what the calculation would be, I enter a script, so my inputs are easy. I do my work on paper, showing you all the work, but then when it's time to enter it, I keep going, enter number, enter.
But the problem is I can't tell if you're doing that from a script that you understand or a script you're just copying and trying to get it from there. And if you were only using a calculator, wouldn't you have to enter all the stuff in anyway? So it has to be fair with other students in the class, right? So for those folks who are using a TI-89 or TI-36, they don't have that advantage to save the time. So that's why you can't use scripts. That makes sense? You may not agree with it, but we're just going to be equal, right? It's fair. And you should say, hey, they could use MATLAB too, but maybe they haven't been spending the time doing it.
That means we don't use command line.
No, you can write scripts in MATLAB if you want.
So we can write scripts live during the test.
Yeah.
We just can't bring it.
Do you know why you're okay to write scripts? Because instead of having to do it in the command line and, oh, I got to make a mistake and I got to go up 10 lines and fix things, you just write it all out. Oh, I made a mistake. Then I can edit that line.
It was just confusing me a bit, because it sounded like on one hand, you didn't want to use scripts at all.
No, no, that's not what I said. I said you can write, earlier somebody asked a question, can you use, you can use.
That's why I was confused.
And I said you could bring in, you can write scripts during the test, but you asked, can you bring scripts to it, which are previously written? And I said, no, I didn't think I was being unclear. If I did, that was not my intent. You can't bring scripts in, but you can write your own scripts during the test. Yeah, that's what I would do. Yes, sir.
Only given 8.5 by 11 sheet paper, could you not only just write formulas but also cells?
Yeah.
Okay,
Yeah,
and you can do it on both sides of it.
yes.
Okay.
But I will warn you, if you have a formula sheet with thousands of pieces of information, your likelihood of success is pretty low. Most of the time, that should be in your brain. Right? And if I needed you to memorize something, or I needed something because you had a lot of, like a periodic table, I'd just give you the periodic table, because I'm not, in the real world, you never have to memorize the periodic table. You just have to know how to use it. No, it's pencil. Everybody who's in the live class will just be given an actual exam. All right, ready to get in some connections? So it's good we cover this, right? Because this is how you connect transformers. In a delta-delta, I mean delta-delta. I look at the YY and I call it delta-delta. It's just two Ys. And everything is in phase, and the turns ratio is phase voltage or line voltage. It's exactly the same. YY transformers are the most common custom connected ones. Like if you were to talk about a three-phase system and you were trying to connect, like if you look at a pole top transformer configuration, if you see three transformers, they're almost always connected YY. Almost always. So here's our connection diagram or single phase equivalent. No phase shift between primary and secondary. And we just have the turns ratio as specified. There are some advantages because you can ground both sides of the transformers, but that's not always advantage. But the biggest thing is there's no phase shift. Here's a delta-delta, very, very uncommon. I don't think I've ever actually, oh no, I've seen one delta-delta. If you look at that, the Millinocket Dolby one, they actually have a delta-delta transformer. So again, the voltages are the same. So the turns ratio is exactly the same, and there's no phase shift between primary and secondary. So over here, if I had to do my equivalent, you would divide by 3 because this is a Y equivalent representation of a delta. Okay. If you want to keep it in a delta, that's fine. Just recognize that those will be multiplied by 3. So that's where the divide by 3 comes from, because you're representing it as a Y equivalent. Delta Y is very commonly used in industry, in industrial facilities, because it provides what's called zero sequence filtering. But you'll notice VAB is across the winding on the high side. Then the secondary side, VAN is here. The actual VAB is over here. So you have a 30-degree phase shift vectorially introduced. And you also have a square root of 3 because this to this transfers by the turns ratio. But going over here, I actually have a multiplier of square root of 3. So I actually end up having to make some adjustments. And you can see my turns ratio is adjusted here, square root of 3, and my 30 degrees in addition to the turns. For current, you also have a problem where you've got a multiplier of my turns ratio, but then I have to divide by the square root of 3, and I also introduce a 30-degree phase shift. So how do we represent that? Same thing, right? We're doing the Y equivalent, so we get a divide by 3. But now inside our transformer representation, the ideal transformer, we have to include the square root of 3 over A. So that's the one thing. And we also have to introduce a 30-degree phase shift. That's the problem with campus. Coming into the top of campus, we have, I believe it's a delta Y transformer that steps down from 46 kV to 4160. At the bottom of campus, it steps down from 1247 to 4160. So somewhere out in the system, they had to step down that 1247 from the 46 kV. So the bottom of campus cannot be connected to the top of campus because there's a 30-degree phase shift, just because of the additional transformation that happens at the lower part of campus. That's been a big issue for 30 years. And whenever you have like a crazy storm that knocks out something on campus, like it's been many, many years, but I don't know, 5 years ago, half of campus was shut down for like 2 days until they started switching some buildings over. But they had to do that de-energized because you cannot connect two systems that are 30 degrees out of phase. So that phase shift is surprisingly a bit of a problem. And people actually have diagrams that talk about phasing diagrams to keep track of things. If you do it from a Y delta perspective, it's the same thing, but you have the minus 30, and notice you don't have to do any adjustments to the impedances. Load tap changing transformers, very, very expensive, but you do find them. Load tap changing transformers are just what they sound like. If you need to, if the voltage is too high or too low on your system, and it's been there for a while, you do a tap position change. Usually you wait at least 30 seconds for the voltage to be high or low, and then you make an adjustment. And it happens under load. You don't have to turn it off. Whereas the transformer that we looked at for the no load and open circuit test, that actually had no load tap changes, which means shut the transformer down completely, unbolt the cover, and then change the tap positions manually by using a bunch of wrenches. Over here, it does it automatically. Very, very expensive, but much finer control. Instead of going plus or minus 5% in 5 steps, including the nominal, this can go plus or minus 10% in 33 steps. So each tap position is about 0.6%, whereas on the other one we had this morning was 2.5%. So not nearly the resolution that you can have. But it's a mechanical process. And that means every time you do a tap change position, you're putting wear and tear into your system. So you try as much as you can not to have cycling of your tap changer. So you have that 30-second deadband saying, okay, the voltage is low or high for at least 30 seconds. Then I adjust, because if it's been there for 30 seconds, it's most likely not a motor that's starting, or somebody switched off a motor. It's going to be more of a longer term one. And you don't have to worry too much about unbalanced tap positions, because most manufacturers have a mechanical linkage between positions so that they're always in the same position. Phase shifting transformers are becoming more and more popular. I looked at a bunch of projects that were in New York over the summer that had phase shifting transformers all over the place. And the reason why we need phase shifting transformers is you cannot directly control the flow of real power through a system traditionally, but with phase shifting transformers, you can do that. So you get a lot more refined power control at the cost of a significant cost. Phase shifting transformers are like 5 times more expensive than regular no load tap changing transformers. They're becoming more popular and more common because the grid has been changing a lot. Like I said, there's a bunch of them proposed for New York, but they have some real challenges with them. Okay. Here is a phase shifting transformer, and you can see you got a lot of cooling over here. And then you have the oil over here. The actual transformer itself is here. And this part right here is the phase shifting part. So look at the size. It doubles, just the physical doubling of size. And it has to use a lot of power electronics. So these are very, very difficult, very, very expensive pieces of equipment.
For those band things.
Yeah, these are radiators. It's kind of hard to tell. I don't think there are any fans in here. They just use natural cooling. So you take the oil and you direct it to the outside, and the oil just has a bigger surface area, so it has a chance to cool. That's all it is. Not a great design, but the nice thing is this is passive cooling, right? Just relies on the fact that at higher temperatures, the density of the oil is lower. So it floats to the top and the cool stuff goes down. And so that gets directed into the transformer. And then the loop just keeps going all over again. You'll notice the pipe goes onto the top, right? So the hot oil goes in over here because it's lower density, and the cold stuff, kind of hard to see. There's a pipe that goes into the bottom. And so it just uses natural circulation to keep it cool. They do have, but not very common, they have forced oil cooled transformers where you actually have a pump that circulates the oil, which does a really good job for heat mitigation, but there's a huge problem with that. If that pump fails, your transformer's in a lot of hurt. So you don't see a lot of forced oil systems because they're prone to failure and they're hard to repair. Over here, I can replace a fan pretty easily. They used to have oil to water coolers that they would actually run water to help cool the transformers, but those are almost all gone because you get some corrosion in the pipe and now you got water going into your transformer. Not a good way to do it. Auto transformers, you see them periodically, again, not nearly as common as a regular transformer. But the primary and secondary wires are magnetically and electrically coupled. They're always magnetically coupled because you have the magnetic flux. But the thing is, with an auto transformer, you have, whoop, I don't know what happened. I'm sorry. Just kind of quit on me. But with an auto, oh boy. An auto transformer does this. And these windings are connected like that. So technically, there isn't even a winding here. It's almost like a tap position off there. So it just drops the voltage. So auto transformers are very cheap because you only have really one winding, but you don't have electrical isolation. So they can make it very, very difficult. But you can have auto transformers that can step up or down very efficiently. But again, remember we talked about, we don't want an auto transformer going to our house because if a fault occurs, you could have live 7160 in your house. Not a good thing to do. That's a picture of the auto. That's it. Not a lot of material today because I wanted to make sure we spent enough time going over the transformer test. And I think we went over like 35 minutes to go through the problem and talk about the test. Questions? Yes, sir. Essentially, what happens, and this is probably going to be a little hard to understand, but what we're going to learn about is power flow through a line. If I look at the voltage here and the angle, I can almost tell you with 100% certainty the power flow going from here to here based on the magnitudes of theta 1 and theta 2. So a phase shifting transformer is going to introduce a phase shift in the winding so that this theta is variable. So it's going to increase or decrease the angle. And it does it through literally just by adding or subtracting some magnetic energy. And it's going to improve or reduce that so you get more power going through the transformer. It's doing it with power electronics, switching on caps and inductors. I think it does it more magnetically than capacitors. Most likely it's done more magnetically, but I've actually never seen a phase shifting transformer. So my best guess is you can use inductors in series or parallel to change the magnetic field. So that's how they work. Not that common. I don't think there's any in Maine. I'm not even sure there are any in New England. I know New York's got a few, but they're not that common. Because there are other ways that you can control power. You might be asking, why does New York want to use so many phase shifting ones? Because all the projects I worked on this summer, they're going to be paid for by the developers and not by the consumers. So it's a way to get really good control at somebody else's expense, right? You bought it. You gave it to me. That's the other thing about all these upgrades to the system. If you want to tie your generator in and the system has to have some modifications made, you pay for those and you don't even own them. You give them to the utility. And you have to pay tax on that because now the utility was given property that's worth some money. So they have to pay taxes on that. It's inventory, right? It's assets. So they have to pay taxes on that. So what ends up happening is you have to do what's called a kayak tax, contribution in aid of construction. You build something and then you pay tax on that to give to the utility so that they can pay tax. So there's a lot of costs that are sneaky costs when you do that. Most people aren't aware. Okay, any questions? All right, that's all I had. So be ready Thursday. Take a look at the review handout. Come with any questions. It should be good to go. Everybody has looked and confirmed, right? They've already looked and seen that material is there. No? Haven't looked? Take a look. worthwhile to spend, I don't know, 20 minutes looking at it to be prepared. All right, folks, have a great day. I'll see you all on Thursday. Take care.